Hi, it's Mr. Benson here again with the second of my videos for life science for chemistry, and this is continuing on from where I was and looking at chemical and physical change. Now the first thing, or where we want to start here, is to talk a little bit about the structure of the atom. So this is something that you're going to look at in more and more detail as we work through the course. We start off the really simple model, and then we move into something that gives us a little bit better understanding, and then you find out that that one's not quite accurate either, and you move on to something better and better until by the time you get to university you've got a pretty accurate understanding of what atoms are made of. I'd just like to point out at the moment that this time that the universe is really weird, and so when you start thinking about atoms, you start thinking about what makes up matter, how the universe works. Pretty strange stuff, and it's not at all uncommon for it to seem really odd to start with. Okay, so the structure of the atom. Atoms consist of three what we call subatomic particles. Now they are made up of other stuff, but we're not going to get onto that. So the main ones are the protons, which are in the which have a positive charge, and neutrons, which have no charge, and they all live in the nucleus. Now these particles have the mass of the atom, so they protons and neutrons have a similar mass, and really the nucleus is all the mass of where pretty much all the mass of the atom is found. Now, one weird thing that was found about atoms a bit over 100 years ago now is that they are mostly not there. So the nucleus is very small and very dense, and the rest of the atom is empty space. So, which means so are we, and that seems kind of weird when you think about it. Now, surrounding the atom, we have these negatively charged particles called electrons, and they're much smaller, about 2,000 times smaller than the protons, and they exist in structures that we call electron shells, and they are at a fixed sort of distance from the nucleus, although it's not so much about distances as about the amount of energy that they have, but we'll come back to that later. So the main thing to remember from this: protons and neutrons in the nucleus. Protons are positive, neutrons are neutral. Electrons, which have a negative charge, are around the outside of the atom in the shells. So we talked a bit about elements earlier. Now the thing with elements, now we talked about this idea that the ones in the same rows had the same properties and that sort of thing. And we talked about the way that a substance is an element if all the atoms in it are the same. Now the thing that makes them the same in terms of their chemical properties is the atomic number, or the number of protons. So when we go back to our element over here, if we were to count the number of protons that were in the nucleus here, that would tell us which element it was. So if you think back to the periodic table that we looked at in the last video, hydrogen was element number 1. It has an atomic number of 1, which means that every atom of hydrogen only contains 1 proton. Whereas if we think about carbon, carbon has an atomic number of 6. Every atom of carbon contains 6 protons. The numbers of neutrons is something that you'll learn about later on. In terms of chemistry, it's not super important. The number of electrons is really important, but again, we'll look at that later on as well. Although I'll give you a spoiler there, it is the same as the number of protons in normal atoms. So if you've got a carbon atom which has 6 protons, it will have 6 electrons. Now, one important thing that we want to be able to do is, when we're describing chemicals, is to use chemical formulae. So this is combining the symbols for the elements and also using numbers to represent how many are present. Now some of these are things that we talk about all the time. So we see Water, for example, most of us know what the formula for that is because, you know, people talk about it. So it's H2O. Now, the question is, what does that actually mean and why is it written the way that it is? So, the first thing is the element symbol. So H is the symbol for, sorry, that jumped ahead on me. H is the symbol for hydrogen. So that's telling us that we've got hydrogen atoms present in the substance. Sorry, I'm having some technical difficulties here. So we've got our H there. Now the two that's written as a subscript, so below the line here, is telling you about the number of atoms that are present that are written before the number. So we've got H2 is telling us that there are 2 hydrogen atoms. O is telling us that there's oxygen. Now there's no number present, so that means there is just one of them. So this is telling us that in the chemical formula for water, there are 2 hydrogen atoms and 1 oxygen atom, and so in each water molecule, that's what we find. This doesn't tell us about how the atoms are connected up though, and that's something else that we'll look at later on. Now, how these substances are formed is through chemical reactions, and we need to be able to describe that in a bit of detail. So when we are causing a chemical reaction, we have substances that are going to get consumed, get used up in that reaction, and they are called reactants. Now they're like the ingredients that we use when we're cooking something. Then we're going to make new substances, and they are called the products. They are produced by the chemical reaction. Now, not everything that we see changing is a chemical reaction. So, for example, if I get an ice block out and leave it on the kitchen bench, it's going to melt. So it's a change, but it's not actually a chemical change. Now, the reason for that is I could, if I get a block of ice and I put it in a cup and I let it melt so it turns into liquid water, if I put that back in the freezer, I can make it into ice again. So this is an example of what we call a physical change. Now again, this is going back to year 7 where we would have talked about solids and liquids and gases, so it's a change of state. But it's not actually changing the substance at all. It's still water, it's just in a different state. So we need to be able to tell whether something is a chemical change or not, and you need to be familiar with this. So, a few things that give us evidence of a chemical change. Production of gas is a good sign. Production of heat or light. So where energy is being released, or actually where energy is being absorbed, can also be a sign that there is a change of state. A change of mass is a really good one. Now that's something that can be very difficult to measure. So for example, in our magnesium experiment, we had a change of mass, but that's because a lot of our magnesium went up in smoke. So we lost it out into the room, but it was actually still there. We just didn't have it in our crucibles anymore. A permanent change of colour. Now the magnesium is a good example of this one as well. We had the change from the metallic silver to the white powder. Formation of a precipitate. Now this is something that only happens when we're working in liquids with solutions, and it's when you form a solid when 2 liquids are mixed. Now the other thing about chemical changes is they can't be reversed. So it's very difficult to turn, reasonably difficult to turn magnesium oxide back into magnesium. It's hard to unfry an egg, which is another example of a chemical reaction. So this is another important thing about chemical reactions, is that all these changes are not easily reversed, whereas when you're talking about physical changes of state for instance, they are very easy to reverse. Last idea that I want to cover quickly as a bit of a revision is this idea of reaction rate. So chemical reactions can be fast or can be slow. So you know of some that are pretty quick. So when we burn something like the magnesium, that burned quite quickly. But if we leave a piece of iron to rust, it can take years to rust away. So that's something that is quite slow. And the idea here is just what we call reaction rate, that some have a fast rate, they happen quickly, and some happen slowly. As you go through science and chemistry, you look at reaction rate in much more detail. There are certain things that influence the reaction rate, and I hope you've done a bit of this in science already to see these things. If not, we could possibly do some. One really important one is the temperature. So when the temperature is hot, the particles involved in the chemical reactions bang into each other more frequently, and they also have more energy when they collide, and that makes it more likely that a reaction will take place. Particle size. So if we grind up something smaller, then we have more surface area to react. So if we want to, say dissolve something, if we drop a big lump in solution, it takes ages, but if we grind it up into fine powder, it will dissolve much more quickly. Concentration, more concentrated solutions contain more reactant particles, so again they're going to bang into each other a bit more. And the last thing that we can do is we can add chemicals called catalysts. Now catalysts are substances which make a reaction rate increase, but they're not actually used up in the reaction, or some of them kind of do get used in the reaction, but then they get recreated again at the other end. So they can be involved in the reaction in different ways, but ultimately they're not consumed by it. Catalysts again are an idea that you'll learn a lot more about if you go on with chemistry. Okay, so hopefully this has been helpful. This is the very basics of chemistry that you want to start off with. There is stuff on the chemistry continuum that starts from this point, but we want to move on fairly quickly to looking at things with a little bit more detail.